second file, this one. So we ask opponent, you have 1 minute to pick a problem to challenge you.
Okay, I would like to challenge problem 11, pumping stroke.
Problem 11, pumping stroke. So the opponent will have a 1 minute to decide.
We accept the charge.
Okay, the problem is being accepted. So, same, I will ask 3 team to write down the name of the presenter on the blackboard. Yeah, please stop.
Okay, so this is pumpkin straw. Okay, could everyone hear my voice? Okay, so this is our outline. So first is problem statement. This is say that a simple water pump can be made using a straw, shaped into a triangle and cut open the vertices. When such a triangle is partially immersed in water with one of its vertices and rotated around its vertical axis, water may flow up through the straw. So we need to find what will affect the pumping speed. Okay, next. This is our theory. So first, you can see this is our status. We call this length L, and this is R. And this angle, we call it theta. We know that R is equal L sine theta. And we can draw this picture. This is straw, and this is water. The water here, there is free force on this water. And we can draw this. This is so first, friction. If friction is this side, is down, we can find that the omega max. Now we are going to find what omega will make that water won't throw up or won't go down. Just stay here. Stay there. So if case 1, friction is down, we can have these three equations and we can solve that and we get omega max. And we can also get omega minimum. Use the same method. Okay. And the next thing we want to know is the speed that water came out from the straw. What is this speed when water threw out? So we know that we have these three lines because this straw is rotating. Okay, and these three lines we can get AX and AY. Okay, we know that, look at this. We know that AY is a constant, but AX, there is an omega squared X. So now we will solve for AX. We let chi equal this thing, and we differentiate it twice. And after some calculate, we know that X is equal to A cosine omega t plus epsilon plus K. And now we need to find what is A epsilon Oh, and K, we substitute this thing as K. Okay. So we know that when the time is 0, that x is, this is water, so x is this. So we know that when time is 0, that x is 0 too. And we know the speed there is also 0. So we can get epsilon is 0 and a is negative k. And now we can now solve for ax, is this one. Then next, because we have this thing, so we can also solve for Vx. So finally we can get this. This is Vx. And because Ay is a constant, so we can use this formula, we can get the Vyr is when the water is on the top, it is just before it go out the slope. This speed is this. So we know that the speed when water go out is Vx squared plus Vy squared, and take a square root. And we know this, so we can find the volume of the water be pumped. So we get this. Look at this line. We know that if the longer this static works, then delta T is bigger, or the bigger the rotating speed is, omega is bigger, or the bigger the hole that water will be sprayed out from it, then that is A is bigger. So the more water will be pumped. Okay. Then our experimental setup. I made this thing. This is floor, and this is motor. There is an axis here, and we add water in this, and this is battle. Okay, and we control the rotating speed by giving it different voltage. So we know that the rotating speed is rated rotating speed times the voltage we gave it is rated rotating speed times rated voltage. Wait. Oh, it's the rated rotating speed times the voltage we gave it over rated voltage. So it is this one. Okay. And we do 3 experiments that the theta is this angle. Theta is 45, 30, and 15. Okay, so it will be like this. Water being pumped. But our data didn't really match our theory. It looked like this. This is rotating speed, and this is the water being pumped. And we think it's because our debits, the throw might not reach the theoretical rotating speed when the motor speed is up. We had to put the damage and let the iron wear at the vertical axis touch the bottom, or it will the axis will rotate it too. This iron wear will rotate, so we have to do so to secure the damage to prevent it from precession. This made the real rotating speed less than the theoretical speed. Okay, so conclusion is, according to our theory, we know that the volume of water being pumped, it can be calculated by this formula. And we know if A, L, or delta T, or omega is bigger, the volume of water being pumped will be bigger too. But our experiment didn't show this clearly due to our damage issue. Okay, thanks. This is my report.
Thank you. So, opponent, please take the floor. Please add some issue question.
This is your page where there is an experiment in the theory. The page when there is an experiment in theory. This. Next page. Yeah, this page. So you say that your experiment didn't really map your theory. What do you think are the variables that are causing this to happen?
I think that is because
You think it's because of precision, right?
it's
The rotating of the axis of the
Yes.
experiment. Are there any other variables that may change the experimental results? Okay, moving on. So, can you turn to your experiment video? The video. Okay. Is this motor have a constant angular velocity? Does this motor have a constant angular velocity? Because it looks like it doesn't have a constant angular velocity.
Oh.
And how can you do your experiment when you don't know your angular velocity? Yes or no? Does it have a constant angular velocity?
The rotating, the
Well,
speed
how do you make sure the rotating speed is like this? Because there is a big difference between you put in the energy and you have in the result. Do you use tracker or any sort of way to calculate the angular velocity and make sure that it stays the same throughout the pumping process? So, okay. And go to your data analysis. So you only do 3 sets of angles.
Yeah, okay. I'm sorry. Time's up. So, opponent, you have 3 minutes to prepare your Please stop.
Okay, I am the opponent of the Winners team, and this is my report on the problem number 11, pumping stroke. Let's look at the problem statement. I think the most important part of the problem statement is the pumping speed. And I don't see that the reporter has talked a lot about it, and I hope to discuss it with him further in the discussion. Okay, here is the outline of the report. There's the problem statement, and talks about some theories, and does an experimental setup to test different angles to explain the phenomenon. Well, it has a static analysis in the theory, and also tries to find the pumping speed through theory, and experiments with different angles, and discusses the precision of the straw to find out why the experiment is different from the theory. Okay, here's the report. The strength is that the reporter has considered many different angles. And there are also some areas of improvement, like how the theory fails to take account of continuity, and the consideration of friction, but not viscosity in their theory. And could use powers to explain the correlation, and not bigger or smaller in their report. Okay, and that's it. Start the discussion. Okay, can you turn to your page where to conduct your experiment? Well, can I ask what are your variables in this experiment that you did? What are your variables?
Variable is the rotating speed of the motor.
So is this a manipulated variable or control variable?
Firstly, control that if the angle is 45 degrees, and
Okay, so what is your response variable? What is your response variable here? Because I don't know.
sorry, it's the water being pumped, and the unit is
What are the units? So you're talking about the response variable is the pumping speed, right? Okay, so how do you measure the pumping speed in your experiment? You can use the story and use the backboard. Okay, you can use the backboard if you like to explain how you measure the pumping speed, because I really like to know. Okay.
every time we let
Okay, can you draw out?
every time we let the motor keep rotating for 5 seconds, and we find how much water is being pumped.
So you find how much water is being pulled out of the container.
Yes.
by the time frame of 5 seconds. Is that correct? Okay, so how would you choose what 5 seconds to try and measure? For in that instance, what do you think about the pumping speed? Is it something like this for the pumping speed stay constant? Is your angular velocity the same for the pumping speed stay constant, or will it change throughout time? Like something like this. Can you draw out a graph to explain how pumping speed changes over time? So is it like this, or does it change with time?
Pumping speed won't change.
So it is feasible to measure the pumping speed with an average of 5 seconds.
Yes, and in the video, it looks the rotating speed looks different. Is because it one part of it is in slow mode.
Okay. So you think that the pumping speed doesn't change really much, right?
Yes.
But as you're proceeding with your theory, the water level actually drops during the experiment. So how do you think it will affect your experiment if you've taken the water level drop into consideration? Will your theory be more complete? Or will it affect the pumping speed? Will it be smaller or bigger? I mean, if you consider the water level dropping, meaning that the water maybe need to get to a bigger height, will it affect the pumping speed? Will it make it bigger or smaller?
I think it won't. Okay. I think.
So when there is more height climb, there might be more energy needed to get here, but the pumping speed will still stay the same. Is that what you're indicating?
Wait a second. I think.
So what is your theory trying to say? Because I don't quite understand your theory. Since this theory may be used in the early stages of the experiment when the velocity of the volume is 0, and over here we look at final velocity. But as your experiment proceeds, meaning that when there is more time frame, you will find that the velocity here is actually equal to the velocity here because of continuity, meaning that the water mass entering the straw and then exiting the straw should actually be the same. So if in that instance, why can you assume your theory in that way? The discussion of continuity should be considered in your experiment. And if it is considered, would you think it will increase the pumping speed or decrease the pumping speed? Or maybe it will be more correlated with your experimental results. What do you think about it? Or do you think that if we consider the continuity, meaning that the velocity enters and the velocity exits is actually the same, will this make the pumping speed bigger or smaller?
I think the pumping speed will be bigger.
Why? Can you explain? Because when we are talking about this phenomenon, I would like to think that there is 2 stages to this approach. Meaning one, to this point there is like no continuity, and after this there will be continuity as the flows becomes more stable. So when you are calculating your time frame, if you want to correlate your theory, you want to measure a stable time frame where it is unstable, and continuity doesn't work. But when continuity, so you cannot do it that way. So you think if it's bigger, then the pumping speed and the time graph should look something like this. or maybe like this. Well, what do you think it should be like?
think this.
Okay, so you think it's why? Can you explain it? Okay, so can you tell me what your theory looks like in this graph? Can you draw out your theory and tell me what it looks like if we want to put a graph of pumping speed? Can you draw out how your theory works? Like, if you're doing a circle, it should be something like this, stay stable. Can you draw it?
I think it will be like it will be constant.
So can you explain it with your theory?
If we look at this, we can see there is no time in
So what is your Vx and Vy? Because in this experiment, we want to measure the water going out of the straw, right?
yes. My Vx and Vy is this is straw, and when water go out, we this is Vx and this is Vy.
So in that instance, you didn't consider it as this.
Oh yes, there are.
You give it a tilted angle, because if you consider your Vx and Vy and you use forces to calculate your theory, you might miss out the N force. That is,
We also consider there. Oh, this,
okay, I can see.
this line is the x and y, but this is
So when you're measuring the V, you're trying to measure both this, and you add it together.
yes.
Okay. So what will so your theory, what you're indicating is that the water going in your straw will increase in speed and get to a maximum speed here and be ejected.
Yes.
Is that what you're saying?
Yes.
Okay, so what do you think will happen if we increase the length of the straw? Will it shoot further? Will it increase the pumping speed?
I think it will increase the pumping speed.
Okay, so also in your theory, you have also talked about the cross-section area of the straw, right?
Yes.
And have you done any experiments to try to prove that your theory is correct? It's the cross-section area of the straw. So it is proportional to the pumping speed,
Yes.
right? So have you tried to
It's to the volume in pump.
volume being pumped for time, and you can do this, and that's the pumping speed. Is that right?
Yes.
So maybe in the future you can do some experiments with area to try to calculate your speed. Okay, so have you ever considered to add pressure to your theory? I mean, water pressure inside the straw. I mean, like, if you have a straw here, I mean, here is an H, right?
Oh,
And the pressure here
we
is,
didn't consider it.
so you didn't consider the new field in every place? You didn't consider it?
Yes, we didn't consider it.
So you didn't consider anything about fluid movements, and you just assume that it is an object trying to move out of the straw, right?
Yes.
Okay.
So sorry, time's up.
Okay, thank you.
So opponent can summarize on this.
Okay, to summarize the report. The reporter has made a lot of theories regarding how an object will get out of the straw when the straw is spinning at an angular velocity. However, in the problem statement, we can find that what it is measuring is actually the pumping speed. And if we want to measure the pumping speed, we should assume that it is a fluid movement, which needs to consider things like continuity and viscosity in the theory. And the reporter didn't measure that. Also, I think the reporter should talk more about how he measured the pumping speed in this report. Because we don't quite know how the pumping speed is measured. And also, the relevant parameters that could affect the pumping speed should also be discussed, since it is taught in the problem statement. Thank you.
Okay, thank you. So, question from the viewer.
First, I want to ask the reporter that do you think the viscosity will affect the experiment? Viscosity, which means that when your water is on the wall of your straw, it will like stick on the straw.
We think it won't affect.
Okay, and I want to ask the opponent, do you think that this will affect the experiment?
Of course, it will affect the experiment. It's something like, because in your report you have talked about friction that may be caused by the water. And water particles, between water particles, there's also friction, and we call that viscosity. Yes,
Okay.
there will be effect.
And I want to ask both of you that do you think that the centrifugal force will affect the experiment? Do you consider the centrifugal force in your theory? Or the reporter first? Do you consider it in your theory?
We think the effect is little, and we can just ignore it. We get this angle is 45 degrees, and we think this it won't affect very.
I think that you misunderstand. So I want to ask the opponent, do you think that the centrifugal force is important in this experiment?
Of course, I think in your theory you have considered the centrifugal force as the omega as this. Well, this is a fictitious force, and like I said earlier, I don't think it is necessarily we can call it the centrifugal force, but more of a fictitious force in this phenomenon. And it may be affected by relevant parameters like angular velocity or the length of the straw.
So the reporter thinks that the viscosity won't affect your.
It will
Do you
affect,
agree?
but it will affect, but it is.
I mean the viscosity.
Yeah, viscosity is how liquids they stick together and there is a force.
We think it will affect, but not very.
But in this phenomenon, if you consider the viscosity, we think that there will be an energy conception. So maybe you can consider this into your
I'm sorry,
theory.
time's up. Viewers, you have 2 minutes to prepare your presentation. Review, please stop.
Okay, I'm the reviewer from Team and Mindao PH1, and the problem I'm going to review today is pumping stroke. And for the current statement, let's give it. And here are some overview for the reporter. His advantage is that it has the details of the theoretical result and the graphs. And here are some suggestions. There is lack of conclusion and making the overall structure difficult to understand or follow. And they didn't have the main focus, so it would be hard to understand and get into the condition so easily. And we think that maybe they should put down the page so that when the opponent is asking questions, the page, they can find the page quickly. And they didn't, and the force is not measured or calculated, which may affect the experiment. And they should have revised their experiment. And here's some overall from opponents. And their advantage is they have confident and calm, and mention variables that the reporter didn't take into consideration. And some suggestions is that they also didn't mention the initial vote. And for the first discussion, the opponent asked that how do they measure the constant velocity? And the reporter says that they control the 45-degree and do an integral calculation. And we think that they need to control the velocity, because the velocity will affect the experiment, and it's also in the current statement, so they need to control it in a better way. And the second discussion is that what are the variables they think. And the reporter says that the rotating speed, which means that the rotating speed will affect their pumping speed. And we think that maybe they should add more variables into the experiment, so that we can make sure the relation between each variables and the experiment results. And for discussion 3, the opponent asks that how do they measure the pumping speed? They say that they measure by how much water pumped when the motor is relating in 5 seconds. And we think that they can measure it in a better way by projectile motion. And they did, and we asked, then the opponent asked that, did they measure the pressure into the conveyor? And they said no. And we agreed to the reporter for this question. Thank you.
I'm done. Okay. The concluding remark from the reporter, please.
So we should check what variable will affect the experimental result and make sure what other variable will affect the pumping speed. And we should use software to analyze the exactly velocity of the water, although it's difficult. The surface tension would not have obvious influence. We think. Okay. That is my concluding remark.
Okay, thank you. So question from the jury. Anyone?
Okay, I have a question for three of you. How do you think, how do you think for the reporters group, how would they measure their pumping speed by using their own experiment? Do you think how can they with this what kind of materials or devices or any other tools that can help them to measure the pumping speed, to measure the water? How do you think? What kind of tools can help you?
你觉得用什么工具可以帮助你测量？这是我的
Okay, you can answer first.
Okay, you can have a small container and a big container. And when the small container is spinning, just take the water out of the big container. And we can measure how the liquids in the big container accumulates over time. And we can measure the pumping speed that way.
Okay.
And we think that we can measure a part time like 10 seconds and how much water that decrease from the mass or the volume of the water.
I think we can add something to water and make the water colorful that we can use tracker to easily track what is the speed.
老师有学生问说组内的
Any other? Yes, please.
And the opponent proposed that the continuity is very important. Yes, I agree with that. And they infer from the continuity says that the velocity in the bottom and the velocity at the top will be the same. Is this correct? Or what makes the difference? We make this assumption.
When the pumping process is stable, it should be natural because the water mass stays the same. The water mass entering the straw and exiting the straw is the same. Well, when there's the same area throughout the straw, the cross-section area is the same area of the straw, it should have the same speed entering and exiting.
And do you have different ideas about it one?
The separation of the water won't be zero, so there must be some change. the change of velocity.
They will change it, but why?
Because the force isn't zero.
Okay.
Could you say the question again?
From the continuity equation, the opponent team inferred that the speed at the bottom and at the top is the same. Is this correct? Or what, under which criteria this assumption will correct? Will be correct?
I think it will not be the same because if the water is more higher, then it must be slower because it needs more force to make it up.
Okay.
Thank you.
Okay. So I have a short question to ask three of you. So, if you want to get the optimized pumping speed, okay, what's the angle, the theta, the reporter say, and the angular velocity you have? So starting from the reporter. The best pumping speed, what's the geometry in your structure? Consider the angle theta.
Our experiments show that this one will pump most water.
Okay, how about the angular velocity? The larger the better, or the small, because they have some limit. Okay, how about opponent?
Well, it depends on what you mean by theta, because in the
Or in the definition from the report.
the definition of the theta will indicate a different height, and that changes two variables. Well, I would do think that with a shorter height, and the theta of 45 degrees as the shortest height, it needs to overcome the less energy. I mean, there should be a bigger pumping speed.
How about the angular velocity?
Well, the angular velocity, I will think that the more linear, yes, according to the reporter's theory.
The higher the better.
Yes.
Okay.
Well, there might be a boundary.
How about the viewer?
I would think that the degree might be 45 degrees.
Okay.
And
How about the
for
angular velocity?
speed, according to the reporter's theory, it if we have more speed, that we give the more rotating speed, the pumping speed will be more.
Do you agree?
In my opinion, I didn't agree.
Thank you. Any other questions? So that's it. go to the comment section and start from the reporter first. It's ratio. So 5, 5, 5, 6, 7. So then the opponent is 7, 8, 8, 8, 8. Then the viewer is 6, 7, 7, 6, 5. Okay, thank you.